Okay, so let's see what we have next. Let V be a finite dimensional vector space over a field F. Let T be a linear operator on V and let Px be the minimal polynomial of T over F. Now, what is a minimal polynomial? A minimal polynomial is by definition a non-trivial polynomial, a non-zero polynomial that annihilates T, which means that if you replace x with T, that means if you calculate P of T, it will be the zero operator. And also it has the minimum possible degree with this property. Now additionally, if you require it to be a monic polynomial, then it becomes unique. So that is our minimal polynomial. Now note that since the minimal polynomial by definition is non-zero and also it's not a unit, let's just think of this polynomial ring. When we studied ring theory, there we determined all the units of this ring, and they are precisely the non-zero field elements. In other words, non-zero constant polynomials are the units in this polynomial ring. Why is this Px not a unit? Well, that's because if you have a non-zero constant and you think of this C as a polynomial, a constant polynomial, then if you evaluate C at T, just like you can evaluate P at T, you can evaluate C at T, that will simply give you just C, and that's of course not equal to 0. Well, that will give you simply C means you will get the operator actually. Here 1 is the identity operator, C times that. That's what you are going to get. And that of course is a non-zero operator, that's not equal to the 0 operator. And that's why such a constant polynomial which itself is non-zero cannot annihilate T, and that is why P cannot be, is not a unit. Here P is not a unit in this ring. So P is neither 0 nor a unit, so we can factorize P. Do you recall from ring theory that this is a Euclidean ring? This is one of the 3 examples of Euclidean rings that we investigated in this text. The first one, of course, is the ring of integers. The second one is the ring of Gaussian integers, that is complex numbers of the form a plus bi, where a and b are integers. And the third one, it's not a single example, but it's a class of rings, the polynomial rings. So these are also Euclidean rings. And being a Euclidean ring, it's also a unique factorization domain. And in a unique factorization domain, whenever we have a non-zero, non-unit element, then it can be factorized as a product of finitely many irreducible elements. Px is one such element. So we can factorize Px like that. And the exact result is lemma 395, which states this. So now we are going to recall this lemma. That means we are just going to refer to it. By lemma 395, we can write Px like this: Q1x to the power L1 times Q2x to the power L2 and so on, Qkx to the power Lk, where the Qyx's are distinct irreducible polynomials in fx, and the exponents are positive integers. Okay, they belong to the set of natural numbers, and for us in this book, natural numbers means positive integers. Something else must also be made absolutely clear here. Whenever we are in a Euclidean ring and we talk about two elements being distinct, usually it's in the sense that distinctness is not literal distinctness, but it means that these, for example, Q1 and Q2 are distinct really means that they are not associates. That's what it means. Do you recall what associates or being associates means in a Euclidean ring? Say you are in a Euclidean ring like this fx, and you have two elements A and B. Say the ring is R. Then they are called associates if A is equal to UB, where U is a unit in R. Saying that these Qy's are distinct means that any two of them are not associates. In that sense, they are distinct. Okay. Now, what are we going to do with these polynomials? Let us next define some subsets of V, subsets of our original vector space V. For each I, consider this Vi. Vi is the set of those vectors V in V on which, if we apply this operator Qi of Ti of T to the power Li, then we get 0. So Vi is such a subset. It is precisely the set of those vectors on which if we apply this operator, then we get 0. Obviously, this Vi is a non-empty subset of V. Why? Because the 0 vector is there normally, naturally. because any linear operator you apply on 0, you are going to get 0. But there may be something else also in this Vi. In general, Vi is a non-empty subset of V, and not just that, actually it's a subspace of V, which is pretty easy to show. The author says so, and I am also saying so. I leave it to you to verify that Vi is a subspace of V. For that, what you have to do, already I have said that it contains the 0 vector. So the problem of non-emptiness has been already settled. Okay. Now you take two vectors from Vi, say u and v, and you apply this operator on their sum. That should give you 0, so that the sum will belong to Vi again. And then you multiply one vector from Vi by a scalar, and on that product you again apply this. That should again give you 0. So the scalar multiple will also belong to Vi. So then it will become a subspace of V. So we just simply mention that fact. Clearly, each Vi is a subspace of V. And something else is also additionally true. Not only is this a subspace, but it's actually an invariant subspace under our operator T. We claim that Vi is invariant under T. To prove this claim, what do we have to do? We will take any element in Vi and we will apply our T on that element, and the result should again belong to Vi. Then it will be invariant. So let U be an element in Vi. So what is our aim? Our aim is to now prove that ut is also in Vi. For ut to be in Vi, what should happen? On ut, if we apply this operator, then we should get 0. That's what we want to show now. Now, ut qi of t to the power li is equal to u qi of t to the power li t. How are we able to write this first and t after that? That's because this operator qi of t to the power li commutes with t. Why? Just think of what qi of t is. Qi is a polynomial. So qi of t is a polynomial expression in t. Say a0 plus a1t plus a2t square, something like that. So whether you multiply that expression by t from the left side or from the right side, the distributive laws and the fact that t commutes with any of its positive integral power clearly tells us that t times this is equal to this times t. So they commute. Now since u is coming from Vi, this will be 0 because that's the definition of Vi. So we get 0 again. Hence ut belongs to Vi. Okay. Hence the claim. Alright. Now, because we have proved that each Vi is invariant under T, so we can restrict T on Vi, and that restriction will turn out to be itself an operator on Vi. This in general is not true if Vi is not invariant. You know what a restriction is. Instead of considering the operator T on the entire space V, we only consider it as acting on a subspace Vi. But whatever input vectors you take from Vi and apply T on that, the output in general lies in V again, because T after all maps V into V. However, the fact that the outputs now lie in particular in Vi tells us that the restriction, if you change its range also from V to Vi, becomes an operator on Vi itself. That's what we call the induced operator, the operator that T induces on Vi. So let's give it a name. Let Ti, let's call it Ti. Let Ti be the operator on Vi that T induces. Now what can we say about these operators Ti? That's what the next theorem is about. So the statement of this theorem is in the context of this discussion. Okay, so it's a continuation. What the theorem is straight away going to say something about these things. So we don't write, we don't start the theorem by again writing let V be a vector space. All those things are already there. And the theorem states this: for each I this subspace Vi is actually non-zero. Okay, I asked you to prove that each Vi is a subspace and 0 is there always. We also saw how it is the case. But actually it has more, something other than 0, at least a non-zero vector. That is one fact. Also, actually our original vector space is a direct sum of these subspaces. Moreover, now we are going to say something about the minimal polynomial of this induced operator Ti. Recall that the minimal polynomial for T is our Px, and after factorizing Px as the product of powers of those Qix, we have got all these things. The minimal polynomial for of same thing Ti over F is precisely this power of Qi of x So this appears in the factorization of the minimal polynomial for t, that is px. Now we have to go through the proof. The proof has some parts. So the proof goes like this. The first part of the proof shows that each Vi is a non-zero subspace. The second part shows that V is a sum of these Vi's. The third part shows that that sum actually is a direct sum. And the fourth part proves this last statement. So that means we have to first show that each Vi is non-zero. But before we see these parts, there is one case which is kind of trivial, which is talked about first. And that is the case when k is equal to 1, so that the only value I can take is 1. If k is equal to 1, then obviously there is only one subspace which is V1. Actually, what is the implication of k being 1? Let's just think of that. Where is k coming from? K is coming from the factorization of px. So if k is 1, this is what px is. Px is a power of an irreducible polynomial. Okay. And V1 turns out to just be V in this case. You think of why that is true. You go back to the definition of the Vi's and see why in this case we have V1 equal to V. But because of these things, whatever we see here are true in a trivial manner. Because our original vector space V, you may remember that we considered V to be not just a finite dimensional vector space but a non-zero space. So this is non-zero. What else? The statement that V is a direct sum of these subspaces in this case becomes trivial. Moreover, the minimal polynomial for Ti in this case is T1, and T1 is just T. The minimal polynomial for T1 according to this claim should be this, which is true because T1 is T and T has minimal polynomial Px, and Px is this. That's why then we write V1 equal to V, and we are done. So we can now assume that k is greater than 1, and with this assumption we now see what comes next. The first thing we are going to do is we will define some new polynomials, call them Hix, for each such I. We define Hix to be let me write like this: 1 less than or equal to j less than or equal to k, comma j is not equal to I, qj x to the power lj. That means for a given such I, Hi of x is actually almost our original Px, but from where we have removed the ith this thing, this polynomial, this power. In other words, if you have, say, your k is 3, okay, let's try to understand the thing like this. Say k is 3, so that you have q1 of x to the power L1, q2 of x to the power L2, q3 of x to the power L3. That is your px. Then what will be, say, h2x. h2x will then be q1x to the power L1 times q3x to the power L3. That means the factor, or whatever you want to call it, which corresponds to 2 is not there. Okay, so that is h2x. h1x will not have this one, but q2 and q3. h3x will have q1 and q2, but not q3. So these are the polynomials hix. Now what can we do with these polynomials? The first thing we note is that since k is greater than 1, so at least 2 such polynomials are there, and these are also irreducible polynomials. So they are not constant. Okay, they are not constant. Why? Why are they not constant? Because being irreducible polynomials, they are irreducible elements in the Euclidean ring Fx. And an irreducible element by definition is neither 0 nor a unit. And the units in Fx are precisely the non-zero constant polynomials. So none of these Qy's is a constant polynomial, a non-zero constant polynomial, and also not the zero polynomial. And that is why each one of them has positive degree. Constant polynomials, those which are non-zero, have degree 0. But these Qy's, being irreducible, cannot have degree 0. They have positive degree. That, combined with the fact that k is greater than 1, tells us that the degree of each hix is less than the degree of px. Why? I mean, if you apply the degree formula to this hix, what will you get? Lj times the degree of qjx, the sum of such terms, from which what you see, something is missing. What is missing? Yeah, instead of just simply saying these things, let me write like this. If you calculate the degree of hix, it will be degree of qjx, where j is not equal to I. So the ith term is missing. However, what is the degree of px? The degree of px, since px is the product of all these factors, where we are not ignoring any term, so it is simply the sum this qjx. Because we are really neglecting the degree of a positive degree polynomial. That is why this degree will be less than this degree. So we write, since k is greater than 1, this is less than the degree of px. Is hix for any I equal to the 0 polynomial? No. Why? Because each hi is a product of positive integral powers of some irreducible polynomials. And irreducible polynomials by definition are non-zero. So the powers are non-zero, and so the product is also non-zero. But exactly why? That's because fx is an integral domain. So when you multiply two polynomials which are non-zero, you again get a non-zero polynomial. So hix is non-zero for each I, and at the same time its degree is less than the degree of px. So if you now evaluate hi of t, can you get the zero operator? No. Why? That's because px by definition is a polynomial having minimum possible degree which is non-trivial and annihilates t. hit cannot thus be, hi cannot annihilate t because of its degree being less than the degree of px and also being non-trivial. So the minimal nature of this prevents hit from being 0. So next we write, hence hi of t is a non-zero operator. Okay. Now, what will demonstrate its non-zeroness? We should get a vector on which when we apply hit, we do not get the zero vector. That will demonstrate its non-zeroness. Thus, there exists a vector v in V such that vhit is not equal to 0. Let us give this vector some, this vector means this one, let's give it some name w. Alright, so now we have got a non-zero vector now, w. Actually this v is also non-zero, but it will not do what we want. W will give us a vector now in vi, in that subspace vi. And being non-zero, it will thus show that the subspace vi is non-zero. So to show that this W belongs to Vi, what should you show? On W you have to apply Qi of t to the power Li. If you get 0, then W will belong to Vi. Let's write what W is. It is V hi of t, Qi of t to the power Li. This is a polynomial in t, this is also a polynomial in t. So they commute, and that is why V Qi of t to the power Li hi of t. Okay. Now what? Now, hold on. I wanted to show that this is equal to 0. Is that what we are going to get? I think I'm missing something here. No, this is not what we want to do, because this will not give me anything. This V is just any V. This V is in no way related to this operator so that it will become 0. Something else must be happening here. Oh, yes. Okay, yes. Yeah, now I get it. You see, if you think of these two things together, you get P of t. Why? Let's just think about it for a moment. With that special case, say we have k equal to 3, so that Px is q2 of x to the power L2 times q3 of x to the power L3. So, just for the sake of specificity, let's think of H2, because that's what we considered there also. H2 of x is what? q1 of x to the power L1 times q3 of x to the power L3. Now, if you think of H2 of t times q2 of t to the power L2, like this one, then you get q1 of t to the power L1, q3 of t to the power L3. That means whatever was missing, we have that again now with us. And this is nothing but P of t. So that's how we have Pt here. This is the only thing that is missing from Px, and that gives us Hit. So if we bring these two things together, we are going to get Pt. But P is the minimal polynomial for t, so it annihilates t as well. So this becomes the 0 operator. Applying that on V, you get the 0 vector. And that's how W belongs to Vi actually. So, W belongs to Vi, but W is non-zero, hence Vi is non-zero. Vi is not the zero space. Okay. So that means we have shown that the Vi's are non-zero subspaces. Next, we are going to show that V is the sum of these Vi's. The fact that it's a direct sum comes after that. For that, what can we do? Note that the polynomials Hi's, H1x, H2x, Hkx are relatively prime. The author asks us to prove this, or at least justify why this is so. It's not something very difficult, but still, let's just see how one can go about justifying this. Suppose they are not relatively prime. That means what? Whenever you think of this type of things, in the background, you can kind of treat them as ordinary integers. That's because most of the things that we deal with when we are in fx and we are talking about the fact that it's a Euclidean ring, what you are doing is, of course, you are doing in fx, but in the background you may think of the ring of integers as if these are integers and as if we are claiming that they are relatively prime, that is their GCD is 1. If you think like that, it will be easier to interpret things. Now, we are supposing that this is not the case. What will be the corresponding thing in the ring of integers? It's like we have a number of integers and we are saying that they are not relatively prime. That means some prime number divides all of them. Similarly here, some irreducible, because the irreducible polynomials play the role of prime numbers in this Euclidean ring. So some irreducible polynomial will divide all of these polynomials. Then there exists an irreducible polynomial, say qx in fx such that qx divides hix for all I. But this qi, since each hix actually divides our original px, so qx also divides px. But what is px? Px is this. And qx divides this. Because qx is irreducible and hence prime, that is why qx dividing this product implies that qx has to divide at least one factor. It's the version of Euclid's lemma for integers in this Euclidean ring. Since qx is irreducible, so qx divides qjx for some j, between 1 and k, you understand. Now qx is irreducible and qjx is also irreducible. Thus qx and qjx are associates in this Euclidean ring. What is the corresponding thing that happens when you are talking about integers? Say you have two integers P and Q, both of which are prime, and P divides Q. What can you say from this? You can say from this that Q is plus or minus P, granted that we do not consider negative primes, but say we considered in the ring of integers, say we do not consider just the positive primes to be primes, but allowed negative primes as well, then this divisibility relation would imply this. But what are the units in the ring of integers? 1 and minus 1. So that's how Q being either plus 1 times P or minus 1 times P makes Q and P associates. The similar thing here is this. So essentially Qx and Qjx are same. The only difference is that that of a unit between them. That unit may be 1 or maybe some other unit in F. But now something will go wrong. Associates means what? So Qx is equal to U times Qjx for some unit Do you see how much we need ring theory in linear algebra? For some unit u in fx, and you know what type of polynomial this u is. This u actually is a non-zero field element, constant polynomial. Now what will go wrong is this, but we have already assumed that Qx divides all the h's. So in particular, Qx divides hjx, right, or u times Qjx divides hjx. Now if you go back and look at the definition of hjx is a product of the powers of the q's, where all the factors are there except this one. However, by the version of Euclid's lemma for polynomials, this means that Qj has to divide at least one of them. And similar to this situation, Qjx must actually be an associate of some other Qi. That's not possible. Okay. Why? Because do you remember that in the beginning when we defined hjx, we said that before defining hj's, actually before starting the theorem itself, we remarked that the Qj's are distinct in the sense that they are not associates of one another. So this is impossible, and that is why the hi's must be relatively prime. Hence, are relatively prime. But that means what? That means that their GCD is 1. Now we know that the GCD of some elements in a Euclidean ring is also expressible as a linear combination of these elements. And the exact result that we have to use here is lemma 394. So by lemma 394, there exist some polynomials which the author has given names AI, A1x, A2x and so on, such that this is 1. So for any vector v in V, we can express V like this. V is equal to V1. This 1 is the identity operator. And that 1 is this. If you evaluate this entire thing at t, you will also evaluate this constant polynomial 1 at t. But when you evaluate a constant at t, we already talked a little bit about this, we get that constant times the identity operator. In this case, that constant is 1, so this is equal to the identity operator. H1 of t plus V AK of t HK of t. Okay, so we keep the calculation hanging here, and now we are going to notice something about the individual terms. What can we say about these terms? Note that the general term is going to look like this: AIT HIT. Obviously, this thing, I mean, if you apply, we don't really know what the polynomial AIT is. It's just some polynomial. Polynomial expression in T, so it's some operator. That operator, when you apply on V, you are after all going to get again a vector in V. So this belongs to V, and so the HIT image of that belongs to this. Okay. However, we have already seen that this thing is contained in Vi. Where did we see this fact? You go back to the first part of the proof where we showed that the Vi's are non-zero. There itself, the clue to this lies. I want you to go to that first part and figure out how we have this containment. So the ith term in this sum is actually coming from this subspace Vi, which means what? It just simply means that if you say write this first vector, I mean after all it's going to be it is a vector, right? the next term is a vector, and so on. If you write this as V1 and the next one as V2 and continue like that, then you have the fact that the ith vector is coming from Vi. But what does this tell us? It tells us that V is the sum of the subspaces Vi. That's the second part. Now in the third part, we are going to prove that this sum is direct sum. To prove that the sum is direct sum, let's consider this. Let this sum be 0, where the ith vector is coming from Vi. We want to show that each ui is equal to 0. Suppose that's not true. Sum ui is not 0. By rearranging the terms, if necessary, we can assume without loss of generality that the first vector itself is non-zero. I mean, actually some other vector may be non-zero, but then you make it the first vector by rearranging terms. So assume without loss of generality that u1 is not equal to 0. Now, what are we going to get from this sum? So, what we are going to do now is we will apply the operator h1 of t on this entire sum, I mean on both sides of this equation. If we do that, we will get this u1 h1 of t plus u2 h1 of t plus uk h1 of t equal to 0 h1 of t, but that is just 0. Now let's just think about the terms other than the first term. Say this term uk h1 of t. If you think about it, what is it? uk q2 t to the power L2 and so on, qk t to the power Lk. That is h1 of t, where except q1 the other things are there. Because these polynomial expressions in t commute with one another, we can bring this qk to the front. Front means just adjacent to uk. Say we have whatever else we have after that. Now because uk is coming from vk, so if you go back to the definition of vk, you will see that this becomes 0. Okay, and on 0 next whatever you apply, whatever operator, the end result is going to be 0. This means that all these terms actually equal the 0 vector. except the first one, about which we are not saying anything right now. So this equation will imply this: u1 h1 of t is equal to 0, and we write the reason also, since uj h1 of t is equal to 0 for j not equal to 1, and that's the justification. But something else is also 0. Since u1 is coming from v1, so on u1, if we apply the definition of v1, on u1 if we apply this, then also we get 0. Now note that q1 of x and h1 of x, these two polynomials are relatively prime. But because in h1 you do not have q1 and here you have q1, a power of q1. Since h1 of x and q1 of x are relatively prime, so are h1 of x and q1 of x to the power L1. It's like saying that the numbers 2 and 3 are relatively prime, and that's why 2 and 3 cube are also relatively prime. It's like that. Alright, so being relatively prime, then a linear combination is one, that thing. So, for some, let's name them Px and Cx, for some polynomials, we have h1 of x bx plus q1 of x to the power L1 cx is equal to 1. Now, u1 can also be written as u1 1. This 1 is the identity operator. And like a previous calculation, in place of this identity operator, we can now write h1 of t b of t plus q1 of t to the power L1 c of t. If you now apply this on u1 plus this on u1 and use these two equations, you are going to get 0. But that's a contradiction, no, because we assumed that u1 is not 0. But this contradicts the hypothesis or supposition that q1 is not 0. So our supposition must be wrong. What was the original supposition? That some ui is non-zero. Thus, our supposition is wrong, i.e. all the ui's must be equal to 0. Hence, the sum is direct. But you may wonder how this implies that the sum is direct. What is the connection? Well, the connection is this. We already know that V is the sum of these VI's. To additionally prove that this sum is direct, what do you have to prove? You have to prove that when you write a vector as a sum of vectors from these VI's, that representation must be unique. Say you have two such representations. Say you have this, where, let me in fact write, for each I, Bi and Ci are coming from Vi. We don't really know whether they are the same or different representations. What does this equation give us? B1 minus C1 plus B2 minus C2 plus Bk minus Ck equal to 0. Obviously, Bi minus Ci belongs to Vi because Vi is a vector space. So this is coming from V1, this is from V2 and so on. So by what we proved here, each of these vectors must be equal to 0. That's why B1 is equal to C1, B2 is equal to C2 and so on. And that gives you uniqueness of representation. That is why this sum is direct sum. And now we come to the last part, where we have to prove that the minimal polynomial of that induced operator Ti is Qyx to the power Li. That's the thing we have to prove. And for that, we consider this fact. Since, let me first write it and then I will explain. Vi Qit to the power Li is equal to the zero space, we have Qiti to the power Li equal to 0. What is the definition of Vi? Vi is this. It's the set of those vectors on which if we apply this operator, then we get the 0 vector. This means that if you are taking a vector from Vi and on that you are applying this operator, you are getting 0. So the image of the subspace Vi under this operator, this you see, this operator actually acts on the entire space V. But in particular, if you restrict it on Vi, then you get the 0 space. So that means the restriction of this operator on Vi is the 0 operator. And that restriction we saw way before when we started our discussion, not today. That restriction is nothing but this, where Ti is the restriction of T on Vi. And that is why this is the 0 operator. Now, what does this equation tell us? This equation tells us that the polynomial, this polynomial, annihilates the operator Ti. When you evaluate the polynomial at Ti, you get the 0 operator. So it's an annihilating polynomial for Ti. So the minimal polynomial for Ti should divide this polynomial. So the minimal polynomial for Ti over F must divide this polynomial. However, it is a power of an irreducible polynomial. It's like the power of a prime number. And what type of divisors do such numbers have? For example, 3q. What are the divisors of 3q? If we neglect the negative divisors, 1, 3, 3 square and 3q. In other words, it's again a power of 3 where the exponent does not exceed the exponent of the original number. Same thing here. In other words, now the minimal polynomial for Ti will again be a power of this irreducible polynomial Qix. In fact, let's just mention that since Qix is irreducible, the minimal polynomial is of the form Qix to the power fi, where the integer fi is a positive integer actually, that's understood, no need to mention that. But what we need to mention is that fi cannot exceed Ly, otherwise we won't have division. Alright. Now we are going to use the corollary to a previous lemma that we proved in a previous video. And that lemma is lemma 661. You see, where are we right now? We now have this fact. We have already proved that V is the direct sum of these subspaces. And we have a linear operator T on V. If you restrict T on V1, you get T1, restricting T on V2, you get T2, so you get these other operators, the induced operators. And you know their minimal polynomials. The minimal polynomial of T1 is Q1, well, you don't exactly know, but you know the form F1. That of T2 is this, that of Tk is Fk. So the corollary to lemma 661 tells us what the minimal polynomial for T should be in terms of these minimal polynomials. That is the LCM of them. So that's where we are going to use the results from previous videos. We can continue from here itself. Now, by the corollary to our lemma, what was the number? 661. The minimal polynomial for T over F is the least common multiple of these. All right. but we already know the minimal polynomial of t. It is nothing but px. So px is equal to the least common multiple of these polynomials. Now if you look at the individual things here, they are relatively prime pairwise. Why? Because these are irreducible polynomials which are distinct in the sense that no two of them are associates of each other. And that is why the LCM will be their product. It's like considering a number of integers which are pairwise relatively prime. Then what is their LCM? The LCM is the product. For example, if you have say 2, 35 and 3, then the LCM of these numbers is their product because they are relatively prime. This one is 2, this one is 3, they are prime, and the prime factors of these are 5 and 7. No common primes. Just like that, the same case here. So now taking everything into consideration, we can write this. Hence, Px is the product of this. I kept some space here because we also know something else. We actually know what Px is in terms of these same polynomials, and that's this to the power L1 and so on Lk. This is equal to Px and Px is equal to this. Now you use these inequalities. Because of the Fi's not being greater than the Li's, what are we going to get from this equation? L1 minus F1, and the other factors also will come like that. Lk minus Fk is equal to 1, and we are able to do such a calculation because, after all, you are cancelling and doing all these things, no? Because you are in an integral domain and you are dealing with non-zero elements, and that integral domain is nothing but this polynomial ring. Now what do you get from these things? Here the exponents are all non-negative integers. Can any one of them be positive? No. For example, if L1 minus F1 becomes positive, then the left hand side polynomial, it becomes divisible by Q1x. Q1x is a polynomial having positive degree, but then it also has to divide the constant polynomial 1. Can that happen? No, because the degree formula will get violated. Degree of fx gx equal to degree of fx plus degree of gx, that thing will get violated. That is why all of them have to be 0. Since Li minus Fi is greater than or equal to 0, we must have Li equal to Fi. So the minimal polynomial for Ti over F is this. And that finally completes the proof. So with this proof over, there is one corollary after this which we will discuss about in the next video. And then the actual Jordan form will come. So let me just end things here itself. Tomorrow we have analysis. And I think tomorrow we are going to discuss, if I am remembering correctly, about integrability of monotonic functions. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.